Thank you, Luke, and thank you to the organizers for inviting me to give this plenary talk on SKA. I just have to say about the previous talk, wow. That's going to be hard to follow, but I will try and do so. So I want to introduce to many of you the SKA. It's a machine being built by radio astronomers, but to do astronomy, and in fact to do physics as well. And I hope to give you some clues as to the sorts of physics and astronomy that we hope to achieve with the SKA. So if we look at the great observatories for the coming decades, there are 4 that you see up there. Top left, of course, I have a picture of the ELT, but I'm aware which continent I'm on, so you know, the Large Optical Telescope could look like that, or even like that. Top right, ALMA, I'm sure you're all familiar with, and I understand Pierre Cox will be talking about the current status of ALMA in a plenary talk tomorrow morning. JWST, we've just heard about. And then in the bottom right-hand corner is an artist impression of what the Square Kilometre Array will look like. And I'll show you more details in the next few minutes. So, what sort of science is driving the construction of the Square Kilometre Array? Well, in the 20th century, I think it's true to say, we, the astronomy community, the science community, we discovered our place in the universe. In the 21st century, it is our intent to understand the universe that we inhabit. So the SKA Science Goals are immensely broad. In the left-hand panel there, you see the impact that we hope the SKA will have on fundamental physics. And this is the physics aspect of the telescope. So we really hope that using the SKA, we will understand gravity at a fundamental level, using pulsars. And I'll highlight the sort of pulsar science that will be possible in a few minutes. Also magnetism, the second of the 4 fundamental forces that the SKA will be able to address. It will be the premier instrument for exploring and understanding the cosmic magnetism and the evolution of cosmic magnetism with time. In the right-hand panel, you see more traditional astronomy subjects, looking at the origins of galaxies in the universe, cosmic dawn, first galaxies, etc. Now, these are topics addressed by other observatories that are under construction or that are planned. But the unique thing about the SKA is we will be using hydrogen to explore many of these things through its 21 centimeter and redshifted transition. In fact, one of the early names for the SKA was the hydrogen array. It was a desire to study hydrogen all the way back close to the Big Bang. That was the original scientific motivation for the SKA. SKA will also have a huge impact on the study of protoplanetary disks, looking at the thermal emission from pebbles and small rocks as stars form. Biomolecules, heavy biomolecules. They have an enormous number of spectral lines in the centimeter wave region of the spectrum. But of course, they're immensely weak, and so you need something of the scale of the SKA to actually detect these. We'll be looking for the signature of glycine, an amino acid. And of course, SETI. We estimate that if technological civilizations like ours exist within, say, 50 light years, and there are many thousands of stars within that volume, with the SKA, we will be able to detect their stray TV signals, their airport radars. Ionospheric radars, such as those at Arecibo, will be able to detect across the galaxy. Of course, it does rely upon such civilizations existing. We just 2 weeks ago now, we had a fantastic meeting in Sicily, refreshing the SKA science case. The first science case was put together in 2004, a 600-page book, but we got 250 people together in the shadow of Mount Etna. You can see behind the conference attendees there for a great week looking at the science of SKA. And we like to put on a show when we talk SKA science. So we did arrange for Etna to erupt, and luckily the eruption occurred right at the end of the conference. Catania Airport was closed the day after most of us had left. So those few who stayed behind for a few extra days holiday, they got caught. It was not a major eruption. Etna does this on occasion, but still pretty spectacular. So I want to highlight two key areas of science. The breadth is enormous, as I've said, but I just want to pull out two particular areas. And one is how we will use pulsars to understand gravity. So the little cartoon you see there is an illustration of a rotating neutron star, the remnant of course, an exploding star. Now, these are cosmic lighthouses, two beams of radio emission being emitted from the neutron star. They're approximately 1.4 solar masses inside 20 kilometers, so it's extreme matter. The matter density is 10 times the nuclear density. Enormous magnetic fields, up to 4.4 times 10 to the 13 Gauss. Voltage drops across the surface of 10 to the 12 volts. And the force, the electromagnetic force, is 10 to the 10, or between 10 to the 10 and 10 to the 12 times that of gravity. And it's a high temperature and superfluid conductor. So not a very pleasant place to be. But the key thing is they are natural clocks with a wide range of periods. So they range from 1.4 millisecond period, that is rotating about 43,000 times per minute, up to 8.5 seconds, that's 7 revolutions a minute. So it's this rotating the clock nature of the pulsars that will be key in what the SKA will be able to do. But of course, pulsars are already delivering amazing science. Now, this is not my science. I haven't looked at a pulsar in my entire life, but I am still blown away by what the pulsar astronomers can achieve. So they are capable of making amazing measurements now with superb precision. For example, in the middle there, you see that they can measure the period of particular pulsars with a 2 attosecond uncertainty. We hear talk of precision cosmology. This is precision astronomy. Measure the actual period of a pulsar, one of its orbital parameters, to a part in 10 to the 10. This is fantastic precision, and it is this sort of precision, the superb clocks that nature gives us, that is the key to what the SKA will be able to do with pulsars to unlock gravity. So, SKA will be undertaking a cosmic census of pulsars. At the moment, there are about 2,200 pulsars known. But we estimate that there are 30,000 normal pulsars that we can see from Earth in our galaxy. 2,000 of which will be millisecond pulsars. These are the ultra-smooth clocks that are needed really to understand gravity. And 100 of them, approximately 100, we estimate will be relativistic binary systems. So that little movie that you just saw there is an illustration of the number of pulsars in the galaxy and what the galactic census will look like. There will also be, with the sensitivity of the SKA, the opportunity to study extragalactic pulsars. So as well as doing pulsar physics alone, the timing precision, which will help with the pulsar physics, but the timing precision is expected to increase by a factor of 100 due to the raw sensitivity of the SKA. We will find rare and exotic systems, including those systems that have pulsars rotating around black holes. And these are the extreme situations, the strong gravity, strong field regime for gravity, where it is expected that the general theory of relativity will break down, and be able to use these superb clocks to probe down to the quantum limit there. Be able to understand the environments of black holes as well, testing the cosmic censorship and the no-hair theorem. But, so that's using the pulsars to explore the gravity in the strong field regime. But also with a network of millisecond pulsars across the galaxy, the SKA will be able to detect the passage of gravitational waves. So we'll be able to see the perturbations in the timing residuals as gravitational waves pass across our own galaxy. Very complementary to the work that Advanced LIGO will be doing, looking at a different regime, different type of object generating these gravitational waves. So this is going to open up a whole new area of physics, studies of gravity. Another area where the SKA, and especially SKA Phase 1, I'll come to the phases in a moment, will have a significant role, is in using hydrogen to study the dark ages, the cosmic dawn, and the epoch of reionization. So the beautiful CMB maps we see from WMAP, from Planck, etc., they display a single moment in the history of the universe. Its initial conditions about 400,000 years after the Big Bang. But what we want to do with looking at H1 through cosmic time is actually trace an evolving movie of the baryonic and dark matter structure formation in the first billion years of the universe's existence. We won't actually be able to get into the dark ages. That will have to wait until we can put radio interferometers on the dark side of the moon, because we will have to go down to below 10 megahertz, and the atmosphere is opaque at 10 megahertz. But if we look at the cosmic dawn and the epoch of reionization, these are going to be broken open by instruments such as JWST, such as the large optical telescopes, and the SKA using hydrogen, the most common element in the universe. So the impact in this area will also be game-changing. The thing about using H1 is that we will be able to do tomographic imaging of the hydrogen looking back in time, effectively using the SKA as a time machine. So that's just a taster of some of the sort of science that the SKA will be able to accomplish. How do we plan on doing it? So I want to take a few minutes now to tell you about the observatory that we plan to build. And first of all, why we're building it where we are. So we have two sites in the Southern Hemisphere, one in Australia, one in South Africa. Why have we chosen these sites? So just consider the hydrogen line, 1420 megahertz, 21 centimeters. As we look back into the dawn of the universe, that the hydrogen, it is redshifted to decimeter, then meter wavelengths. So looking back in time, the wavelength of hydrogen changes like this. Unfortunately, that's where mobile phones, aircraft, digital TV, and FM radio sits. So I'm afraid you, humans, are the enemy of radio astronomy, the enemy of our ability to probe the early reaches of the universe using the hydrogen line. So we have to get away from people. So we looked at several sites around the world, and we found two superb sites. Now, they're not perfect. I don't think any site selection process is ever perfect, but these are pretty damn good. So in South Africa, about 800 kilometers northeast of Cape Town, we have the Karoo Radio Astronomy Reserve. For those of you who've used the SALT telescope and the other telescopes down at the South African Astrophysical Observatory, that's at Sutherland, which is a couple of 100 kilometers away from the core of the SKA site near a small town called Carnarvon. So it's a very sparsely populated area, but it's still relatively accessible. On that site already, our South African colleagues are building MeerKAT, which is what we call an SKA Precursor. So this is a 64 antenna array, 13.5 meter antenna, offset Gregorian design, as you see in the picture there behind me. This was taken in March of this year. This is the first of those antennas erected on the site, 63 more to follow, and it is expected that the array will be operational in 2017. This is a precursor to the SKA. It's actually establishing much of the infrastructure. I just have to show you this next picture. That's not an artist's impression. That's a photograph. I think it's a beautiful photograph of a radio telescope. Nicely backlit, of course, but you can see the galaxy and the Magellanic Clouds lying above it. In Australia, our Australian colleagues have established the Murchison Radio Astronomy Observatory in Western Australia, about 800 kilometers north of Perth. Again, actually coincidentally, there's a town called Carnarvon in the same general area. But the Murchison Observatory is even more remote. You can see it on the map there, about 350 kilometers inland from Geraldton on the Indian Ocean coast. Very nice spot to visit. But the Murchison Radio Observatory lies in Murchison Shire, a county which is about the size of the Netherlands, with a total population of about 100 people. We know them all. In fact, we had a neighborhood barbecue there a couple of years ago, and most of them came by. But it's important that you know your neighbors, especially out in regions like this. So these are two of the most radio-quiet sites on Earth, and that's why we're there. It comes with logistical difficulties. To get out to the Murchison site, for example, there's 150 kilometers of paved road and then 200 kilometers of dirt road, although the Western Australian government is upgrading that for us. And the local residents will benefit, of course, as well. So at the Murchison, the Australians have already built a 36 antenna array, the Australian SKA Pathfinder. This is an aerial view of the central part of it with the high-tech radio frequency interference shielded control building there. On both sites, on the MeerKAT site and on the Australian site, we can be our own worst enemies because we will have massive banks of digital electronics in those control buildings, and we've got to keep that shield the telescopes, the sensitive receivers, from that interfering emission. So very cleverly designed buildings on both sites. The Australian array is built, receiver outfitting and commissioning is underway. This is what the antennas look like, 12-meter, 3-axis antennas. And right at the focus there, you see what's so special about ASKAP in particular. This is a phased array feed. It's actually it's the radio equivalent of a CCD, but it gives enormously wide fields of view, 30 times the area of the area of the full moon. And so it gives us a fantastic survey capability if this technology can be adopted for the SKA. They are actually already doing science with just 6 antennas equipped with receiver systems, these phased array receiver systems. So this is a 9-beam image. ASKAP is capable of recording 36 beams, 3 by 3 square degrees, single 12-hour observation, and several hundred radio sources in there. This is just coming out of the commissioning observations. So work is happening on both sites. We're going to build on that. Also, there's a third precursor, a low-frequency precursor, the Murchison Widefield array, also on the site in Australia. These little spider things here are low-frequency antennas to look at hydrogen and synchrotron emission at very low frequencies. So they're only about 1.5 feet high, 16 of them in this picture, and there's 128 of these tiles. No moving parts. This is a radio telescope for low frequency. We'll have an adaptation of this for the SKA. So, phase 1 of the SKA, which will be about 10% of the total collecting area. 2 sites, South Africa and Australia. On the South African site, we will build what we call SKA mid frequency, which for us is somewhere between about 450 megahertz and 3 gigahertz initially, but we will go to higher frequency. So we will build 190 SKA dishes and add them to the MeerKAT dishes on the site in South Africa, producing about 250 dishes. In Australia, there'll be 2 telescopes. We're building 1 observatory and 3 telescopes. One of my optical colleagues in the UK says he thinks us radio astronomers have been brilliant in persuading governments to fund 3 telescopes at once. But low frequency, these are the low frequency dipoles. We estimate that we will be building 250,000 low frequency dipoles. These are about 2 meter tall Christmas tree-like antennas. They're the evolution of the things I just showed for the MWA. And then also in Australia, incorporating the 36 ASKAP dishes, there'll be what we call SKA Survey, using the phased array feed technology, wide field of view, adding 60 SKA dishes, producing a fantastic survey capability. So the cost cap will be of order 650 million euros for SKA Phase 1. We've decided, because of the inherent scaling ability of interferometers, that we will set a cost cap and we'll work towards that, and we'll build as much as we can afford in the first instance. Construction from about 2017 till 2023. My final slide, I'll show you the broad schedule. But early science in 2020. Like ALMA, we'll be able to deliver science with a fraction of the array built. SKA Phase 2 will be considerably larger, up to 2,500 dishes and up to 3,500 kilometer baselines in Africa. Of the order of 1 million dipoles spread over a few hundred kilometers in Australia. And then of order 250 what we call dense aperture array stations. This is a new technology that can see all of the sky simultaneously. One of its principal science goals will be to do a 1 billion galaxy survey in hydrogen. Construction for that, latter part of the next decade. We've got to build SKA Phase 1 first. Just to give you some idea of the impact of SKA, this is one measure, the survey speed. This is a log scale on the left, and of course frequency across the bottom. You can see LOFAR and the JVLA, the 2 best instruments in their frequency bands now. SKA Phase 1 will be a factor of 10, 20, 30 faster in survey speed than the current instruments. SKA Phase 2, enormously more capable. So, the current status of the project in the last few minutes. We have 11 members of the organization at the moment, many of them represented by their government funding agencies. At the moment, we're structured as a private limited company, but we're looking very hard at developing a treaty organization for a 50-year project. Our member countries insist that we have a robust structure, robust governance structure. We have an international design team based at the SKA headquarters at Jodrell Bank, Manchester in the UK. We have approximately 500 engineers and scientists around the world designing the SKA at the moment. And we have more than 150 million euros committed for the 4-year design program, which is well underway. SKA will be built by industry, though. The scale of it is much more than individual observatories or research organizations can manage. We have 11 design consortia. I won't go into them. You can find the details, very readable descriptions on our webpage. But these are the sensible consortia you would put together. You have one designing the dishes and receivers, one doing the digital electronics, one doing the infrastructure, etc. We are driving development in many different areas. We are going to build initially 250 and ultimately 2,500 dishes. Signal transport, 10 petabits per second we'll be looking at. That's more than 10 times the global internet traffic of the planet. We will have to generate that data and process that data. So we're going to require enormous signal processing capability and software engineering and algorithm development to handle the flow of such data into our supercomputer. Data storage is an issue, power is an issue. Nobody ever said a project like this would be easy. So the current status is we did very well last year. The plan that we put together at the beginning of the year, we met all of the milestones. Early this year, we were very pleased when the UK committed £100 million. That's 125 million euros. So that's 15% of our capital cost for construction. That was a very nice result. We're working with other countries to deliver their commitments. We've just had the big science meeting in Sicily a couple of weeks ago, and in November of this year, we're looking at the preliminary design reviews of all of the various elements. Then we have this thing called rebaselining that you may hear about. This is to scale the SKA to fit within the cost cap. So that's going to be an interesting process. The schedule, you see here the schedule for 10 years from 2013 to 2023. We're about here now, so the preliminary design reviews will be starting later this year. There are two key milestones. The first is this rebaselining that I've just mentioned, where we scope the observatory to fit within the cost cap. And the second there is the approval for funding, for construction. That is where we have to have the majority of the money committed. We know where it's coming from. We know what its our funding profile will be, so we can proceed to construction. 2017, we're putting a year aside to go out to tender and procure contracts with industry to do the construction. Industry is already engaged heavily in the design process. And then we hope to start construction in early 2018 on both sites. And as I said, early science in about 2020. Thank you very much.